And I hide floating menu. Just to double check, so let me see if I see. Where do I see? Here it is. Can you please confirm that you see my screen in Zoom?
Yeah, we can hear it.
And but do you see my screen?
See it.
Okay, good. So now people here should also see my screen. What? All right. Hi, folks. How are you today? Good. Great. Nice. Yes. So let's continue our course, and today we will be taking a boot camp on fundamentals of machine learning. But of course, I want, well, I will tell a little bit of trivial things, but again, just to be on the same page, we will be talking about very important things, distances, or I mean, what is the difference between different ways of measure distances between samples. We will be talking about how to assess accuracy or performance of classifiers. And last but not least, we will be talking about the approach to experimental evaluation of classification models. And again, I'm pretty sure you did some modeling, machine learning modeling before. But what I will tell today, I will try to put it in the context of your mini project. So, in particular, talking about experimental procedure, I refer to first the article, your starting point for the mini project, and specifics of the data sets. And I also want to kind of make this class somewhat more interactive. So I will ask questions, maybe. So if you say, if you think that it's obvious and you know it, so just shoot and reply. We begin with something which is still quite generic. We will begin about just laying out the landscape of methods that are used in the context of different machine learning or AI tasks. So let me see. Let me first try if you see something on the screen. So two. Again, to link somehow material of this class to what we talked about yesterday. So we are talking about an abstraction which is called AI agent. And AI agent interacts in a bidirectional way with environment. And so we are talking specifically about intelligent agent. It means that so it can convert the sampled environment into kind of abstractions. So and then these abstract concepts, they are input into, well, let's put it as a kind of course name, knowledge management and reasoning. Engine, so to say. We are not talking about this left-hand side part. We are concerned about really analyzing the environment which we sample through our available sensors. And we got, and starting from this point, we operate on data. So here, if we zoom in, so we sample environment and convert to data. And we do a process, I mean, during this transformation to abstract concepts, we do process this data with a specific algorithm for which serves given purpose. And again, so the obvious difference, the semantic difference between machine learning and AI is that in machine learning, our algorithms or a particular algorithm serves a specific purpose. So we want, for example, to classify, we want to predict on data, etc. And practically, so there are several algorithms that can serve same purpose, and they may have different complexities. So let's talk about landscape of AI or ML algorithms. So so if we talk about different algorithms, so we can make some taxonomy classification of them depending on the complexity of the underlying data. So here we are kind of the question is, what does it mean? A case where we have a simpler data versus the case where we have more complex data. So simple data, or by simple data, so I mean the cases with well-defined attributes. So when a phenomenon can be characterized or sampled via a well-defined attribute or features. So features. So basically, the case in a very simplest form, so, which can be described by a tabular, so table with different fields, each field corresponding to certain properties. Like in lab for unsupervised learning with self-organized maps, you will be working with a zoo data set. So basically, classification of different animals, and the attributes or features are kind of whether an animal has a tail or not, has a feathers or not, etc., etc. For and such. So this is an example of simple data. More complex data is the case where there are no obvious features. And a typical example of it is like an image. So you have pixel intensities. There are many. There is no structure, predefined structure in them. So you cannot extract any particular pixel that is characteristic for a given class. And actually, depending on the case, you can, I mean, this is the first rule of thumb, which methods you probably want to use out of all different possibilities. So if we have this ML algorithms, so then the case with simple data, so it brings us to the domain of what is called classical or a classic ML. And again, so now talking about different tasks. So if we have, so we can talk about supervised versus unsupervised methods. So if we go to supervised case, so we have two possible tasks: classification or regression. Can you name some classical machine learning methods suitable for classification, solving classification tasks? SVM, yes, absolutely. More? KNN, great. KNN, yes, absolutely. That's the best one, the easiest one. More? Decision trees? Okay. So let us first kind of cast some instances, and then we will do some reflection on it. So in regression domain, so these are the instances of algorithms. In the regression branch, or for solving regression tasks, we have linear regression, polynomial regression, ridge regression, and such. Linear, ridge. Ridge is a regression with the regularization. So yes. So that are some of the options. So if we talk about unsupervised cases, so we have here two main branches that you have to be aware of. So a branch for clustering and a branch for dimensionality reduction. So for clustering, so can you name some approaches?
K-means.
In Zoom, what did you say?
K-means.
K-means, absolutely. Isolation, forest, yeah. And such. Dimensionality reduction. Very seldom people attribute it to learning. It is learning, so it's learning very essential properties of your data. So PCA, yes, more. Disney, that's really good. Yes, that's also learning. Yes, I mean it's for visualization, but it's that's good. SVD.
LDA.
Yes, of course. That's yes. Latin discriminative analysis. Yes, and such. Very useful techniques that shouldn't be forgotten when you work with data. I will not go into details explaining all of them. But I mean, you should know that they exist and use and have it in your possession as a tool. So let's and then here we also have this reinforcement learning, so it's part of classic ML. But let's not elaborate more on that. But let's now think about complex data. So complex. So the case of no obvious features. So here, it is here we talk about artificial neural networks. So basically, I mean, one of the sayings in the ML community is that whenever you don't know anything and you have no clue about your data, then you choose artificial neural networks and hope for the best that they will be identified. But they are very good. They are very good tools. Of course. So, and here again, so we have number of techniques, a number of algorithms serving different purposes. So for classifications tasks. So for classification, so we have what? Our MLP, multi-layer perceptron. CNNs and such. We have a number of approaches for unsupervised learning. So here we have self-organizing maps. What else? Autoencoders. And such. And then networks which are suitable for analysis of time series, again, in different for solving different tasks, both regression and classification tasks. Recurrent. So here we have this LSTM and echo state networks. or extreme learning machines, or some others that we will try. So this is a really rough landscape of available solutions. So again, now talking about AI and using AI for solving practical tasks. I don't know. Tell me if I'm wrong, but I mean, the tendency is to jump immediately into PyTorch and start to configure different complexity convolutional neural network and try solving it. On the other hand, I hope so. I didn't tell you yesterday, but I will. I have plans to invite to invite representatives of a company doing machine learning for security purposes here. So it's a startup. It used to be a startup originated here at LTU, and it is called BehaviorSec. I don't know if you heard about it. So they did behavioral biometrics. So and again, you will understand now where I'm heading to. So the idea is that whatever you do with your computer, like the way you type, the way you move the mouse, the way you scroll the pages and in your web browser, can characterize you as an individual. And so their product was about collecting the statistics, user statistics, and making a prediction whether it is you or not you. So user identification. And their product, for example, runs by many Swedish banks, and not only Swedish banks, different European banks as well, on the background. So whenever you try to log in, so they try to monitor the way how you type passwords, for example, and such. So as an extra precautionary measure. But why am I telling you this? So this is a typical machine learning task and big data case. So you have plenty of measurements. You need to identify. You need to take complex decisions. So the long story short, they never consider ANNs, neural networks, for their purposes because they're so heavyweight. So their solutions were based on k-means clustering and random forest decision trees. So that when meta comes to, for example, online predictions. So again, the message here is that when I approach solving a particular task, so consider all possibilities and choose the method that suits the needs best. So that achieves best balance between performance and efficiency of computations. So let me see if I will to reshuffle a little bit the presentation flow. That I will come to later on. So let us talk now about the general approach to solving a machine learning task. So to create to create and evaluate a data-driven model. Yes. So your data. So basically your input is the data in the following format. Well, let's put it this way. In general, to solving ML task. So your input data. Is either in a form of sequence, if you talk about, for example, time series, but then we talk about dependencies, time dependencies. We will come to this case later on. So today we will be talking about a rather specific case where your input data is a collection or is a set of attributes. In general sense, or features synonymously. And this set, so you normally the set of attributes is represented as a vector. So so normally used by denoted by bold letters. So where you have a specific values for this for different attributes as the components. And this construct is called a feature vector, obviously. And then dependent on the task. So this feature vector can be accompanied with an information about belongingness to a category. So if you talk about supervised learning, or not, if we are in the domain of unsupervised learning. But nevertheless, so what you have as an input is a collection of these feature vectors, which is a data set. So collection of feature vectors. So far, quite obvious information. And now we need to, our task is to take this data set and select an algorithm that is suitable for solving a particular task. And do what? And verify and test performance. So it's quite straightforward process. Take data, put in into the algorithm and test performance. Obvious, if not, the algorithm would be characterized through a set of parameters that actually affects the performance. And these parameters are called hyperparameters, right? So your task as a machine learning AI engineer is to identify the proper algorithm, but also to tune its parameters so that it produces best results for a given task. And now we are entering a domain of systematic experimentation. And now, so starting from this point on, I want to talk quite subjectively or objectively, rather, for the case of these data sets that you will be using in your mini project. So UCI 121. So experimenting with 121 UCI data sets. So what is so special? I don't know. Did you read the article since yesterday? Did you download all the 121 data sets? No. No, not yet. Okay. But again, so then you can use this information as a guideline. So what to look at. So before going into the peculiarities of the specific data sets, let us identify two main phases for selecting optimal configuration of hyperparameters. So I probably need to annotate here that the task of ML engineer is to select best configuration of hyperparameters. So again, hyperparameters, they are specific to particular algorithm, of course. So what it can be in the case of neural networks, I mean, as closer to our body. So what are the hyperparameters in if you, for example, choose to go for multi-layer perceptron for solving classification tasks?
How many layers?
How many layers? What is the size of the layers? What is the nonlinearity function you choose, and etc., etc. So some of them. So by configuration, I mean the combination, so particular instantiation of these parameters that achieves best performance on a given task. And here we enter into the common approach for doing this task, which actually includes two stages or two phases. So first phase, data splitting. And second phase, data standardization. Or, sorry, I mean, that's just one instance of data pre-processing. So you will try different pre-processing techniques in lab 1. Data splitting. So what do I have in mind here?
That's maybe validation set. Okay.
Maybe validation set. Absolutely. So test. Oh, sorry. Train validation test. So what is a general rule? What are the main properties for say train and a test set? The ideal yeah.
The algorithm should never see the test set.
Exactly, and formulated in I mean, in other words, train and test sets should be independent. from each other. So test set should never be touched. So and in this case, so what would be the procedure for selecting the best configuration? So assume now we have this ideal split on train validation test. So the general procedure is about doing the following. So you do you train your algo for different configurations. For different configurations of hyperparameters. And you to understand which configuration is better, so you use validation set, obviously, right? So assess performance. Yes. What do you do then? Retrain for yeah. You train and retrain and finally you select the configuration which performed best on the validation set. Next, so what you do? So you take best configuration from here, and now you retrain exactly. You retrain for this best configuration on the train set, and you test on the test set. Take best config, and for this configuration, you normally you need to retrain because you don't keep because of memory reasons you don't keep the previous models. If you do, then you just choose the one, but you retrain for this configuration set and test on the training set on test set. And talking about UCI 121 data sets, only 19 of those have clearly separated train and test sets. Only 19. So you will see two different files. One is train, well, clearly marked as train, and another one clearly marked as test. So, and then you can read in the paper, so the approach to for training classifiers. Normally, in this case, so there is no clearly separated validation set. So what normally people do, they take the train set, split it into two equal parts. So one is used for training, another one is from the training. From the training file, you split it into two equal parts. At least that's what they use in the papers. Use one for training, one for validation. And then to test for this final test, they retrain for the best configuration. They retrain on the entire training set. So they don't use it. They don't leave out the validation set. And test on the test set. So let me see. UCI 121 the sets. 19 separated. And 102 known separated. What I mean, so it's a single data file. Accompanied with a index file. And it is here you have to be careful and systematic when performing splits. There are different ways for doing so. So in this paper, you will find an approach which slightly deviates from so-called from what one would see as a common approach. So let's talk about this non-separated data sets. Splits of non-separated sets. So here there are different approaches, but from the applied point of view, so if you, for example, want to compare your performance to some other people's performance, you probably, again, so you at least you need to read carefully their way of assessing the performance so that the results are comparable. So what they do, for example, so they take this single file. So this set, and for training purposes, they split it into 2 equal parts for on train and validation. For train and validation, and then the procedure is pretty much same. I mean, so you use train and validation parts for finding the best configuration of hyperparameters for given algorithms. But what about testing then? So we don't have a test part, and this is somewhat unconventional. So what they did, but again, for the purpose of compatibility, so it is reasonable to adopt same approach. So so these 2 are used for training. For testing, what they do, they adopt 4-fold cross-validation. So it is same data, but it's now used for testing. So they split well, 4 times randomly in proportion 75% for train, 25% for test. Train a classifier for best configuration of hyperparameters, test on the test fold, and repeat it 4 times and average. So as I said, you may figure out yourself. So that is a rather problematic approach, because I mean, in this approach, you do not have a separated independent test set. But well, again, for compatibility reasons, you may use it, or you should at least indicate how your approach is different from the one adopted in the paper. So just to summarize, for testing, for testing, the entire data set is used in 4-fold cross validation. Cross. Right. Because I mean, what is the difference with from the traditional approach?
The difference is that they allow the algorithm to see the test or see the data they are testing.
Exactly. So you, I mean, it's immediately kind of subjective to something which is called data leakage. So you test and train on the same data. Sometimes you cannot avoid it, especially if your data sets are small. But you should be aware of what you are doing. Let's take a short break, and after the break, we will talk about the second phase, which is connected to the first phase, which is data pre-processing. So 5 minutes break.
Det var en snabb fråga
Ja.
om labbarna. I en av slidesen igår
Ja.
stod det att man kunde jobba på.
Ja.
Är det representerat i rapporten också, eller är den individuell?
Jag skulle önska mig att ni gör
Det skrev jag också att rapporten och den här Python-filen ska också vara som en rapport.
vad sa du?
Det skrev jag också att Python-filen skulle vara som en rapport också.
Python-filen? Jo, men det är klart. Så det är Jupyter Notebook som gäller. Så jag annoterat.
Hur du tänker om man kan göra lappen och programmera tillsammans, då kommer man skriva rapport.
Ja. Nej, men, det går bra. Alltså, jag ska rätta till. Så att, men det är viktigt att var och en skickar in rapporten. Så det är att inte det är inte gruppenlämning.
Nej, men det har bara om vi har samarbetat. Så
Absolut. Så, se bara till att ingen rider på...
Nej,
jag köper det. Så det är en av de effektivaste sätten att lära sig förstås.
Vi vill bara klara upp det.
Det går bra. Det går bra. Yes. Det är en matris. Ja.
Problemet
Och
är
då
att
har vi tre matriser. RGB. Och sen så har vi en gånger tre matriser. Så det är en tensor. Det här är en tensor. Så det är en multidimensionell.
Ja, men X är väl alltså höjden?
Det är inte en siffra.
Är det som det här är dimensioner?
Om till exempel vill jag säga bild är kan det vara då blir det och det här 5 stycken bilder. Då blir det en array. 5 gånger 124 gånger 4 gånger R gånger en bild.
Ja, precis.
Så en matris på R, en annan matris på B, B. Och då kommer den här 5
Jo, ja men okej. Jag kan få lista på det. Nu har jag arbetat med det här i jag har tagit fram bilder av vad
det kanske gjorde det.
Som det ser ut nu så har jag en sån här om du tänker en samtal det är bara
Jo, men jag menar
jag tänker att X är precis en är indexen på bilden och så har vi X det är höjden på bilden och så Y bredden på bilden och sen sista siffran är
UCI har fel hemsida på datadokumentet.
Dimension nummer 2, det är 2 dimensioner. Här. Så du har en bild. Jo. Som egentligen är
jo, men precis R och G och B.
R och G och B. Men det är R och G B. Men det är en bild så det är med dimensioner X och Y.
Yes.
Men det här är en matris, va? Så det är med X antal pixlar. Så det här är notationen. Så 1 gånger X gånger Y gånger 3. Det är bara
jag tänker
notering för sammanlagt 3 stycken array och gånger en.
Ja, men precis. En är hur många bilder man har.
Ja.
X.
Men du säger storlek på
precis, men du säger att X inte bara är en siffra då. Du säger att det är
det är en dimension.
Jo, det blir ju en siffra i den här arrayen som vi gör. Alltså det är ju...
Nej men jag menar det här är notationen. Det är dimensions.
Men den här trean då representerar Varenda sån här liten punkt.
Tre,
Ja, så den här punkten har värre. Ja, men okej, det har jag tänkt så. Sen är det ju att vi ska, jag kan inte ställa den här frågan sen om vi ska fortsätta, men i den här preprocessing tutorialen så ska man ju leta på covariance matrix och sånt där. Och då kräver de ju 2 dimensioner.
Då kan du kan det kallas för nej. Man gör flattening. Man gör preprocessing per komponent. Så man normaliserar R per G. Och man kan med bilder man brukar även det som kallas flattening. Gör det till en dimensionell man kan jobba med 2D.
Men då är tanken att man gör det för varje RGB.
All right. So let's continue. So that was the story about data separation. Looking a little bit forward. So now we will be talking about peculiarities with data pre-processing, which is also connected to data separation, which at the end also will result in a number of experiments that you need to perform to systematically assess accuracy of your algorithm. So again, I will not spend time on different techniques for pre-processing. Maybe I can ask you, so why do we do pre-processing?
To streamline the process for the algorithm.
Oh.
Streamlining the process for the algorithm. If we have like pictures, some pictures might be different size, and we have a fixed set of neurons, the inputs.
But if you think about, for example, yeah, that's for sure. I mean, so if you want to do some rescaling or resampling, that's part of pre-processing, of course, in images. But if you think about the values of each feature across different samples, so why do we need to do pre-processing?
Could it be to restrict our data?
Huh?
Could it be to restrict our data because you have so much data?
No, I mean the first part is okay. So yes, we restrict. Yeah, or we rather need to harmonize it so that it satisfies certain properties. And again, the long story short, different algorithms make different assumptions on the data that comes in. So again, the very simple intuitive example would be, again, from the neural networks domain. So you choose one or another non-linearity function. For example, you will be working with sigmoid and ReLU in one of the labs. So now think about the case where you have all positive data. So that's totally valid. So your intensities are always positive, right? So from the point of view of non-linearity then, so the non-linearity, especially, for example, ReLU, so it zeroes all, I mean, that's the idea with non-linearity. So you kind of get rid of some information to smooth the overall function. So ReLU simply wouldn't work on all positive data. So there is nothing to cut in this. So by definition, so your data need to fed into a specific algorithm according to the mathematical functions that do transformation from this data. And of course, well, there are different techniques that you have to do. At least we will be talking about standardization. In standardization, this is almost must have with whatever data you do. So it's a zero mean transformation and making variance of one. Variance of data one. So you define by divide by standard deviation per feature. So you have features. X1, Xn, 1, X1, Xn, 2, etc., etc. So each feature, well, it's rather independent coordinate again. So you especially if you do some dimensionality reduction, so you remove the relation between features. So they are kind of independent from each other, but so they still can have different mean and variance characteristics. Why? Because those are measurements. Those are your measurements of the phenomena that you are looking at. One X, it can be temperature measured in Celsius between 0 and 100 degrees. And another is a pressure in kilopascals or whatever. So, I mean, they're all different. And the algorithms, on contrary, they, let's put it in a very non-technical way. So they like standard harmonized range of values and harmonized characteristics. So they are all in the same range, centered with certain variance characteristics. Yes, and so to harmonize data across features. This is somehow I will link later on to. I mean, one of such requirements are placed by the distance measure that you use. I mean, in many models, we will be talking about it. You use distance to measure the proximity of two data vectors to each other. And by the proximity, you decide so whether it belongs to one category or to another category. And in the first place, the measure of distance can be very sensitive to differences in absolute values. So, in this case, so if you have one feature which is in the range, say, several hundreds in values, and all other features are around 0, so your distance metric will favor, will work mainly on that outlier feature. I mean, outlier, not harmonized feature. So that's one of the simplest intuition behind standardization. But then you also, I mean, in lab 1, you will try whitening and other stuff that is used for pre-processing. Yes. How to standardize then? So what does it mean? So it means that you take some data and basically compute your parameters for the standardization. So you compute a mean, for example, you compute a standard deviation. So per column, so column wise, like mean STD, right? And then you kind of, I mean, the Z transform, you just minus mean divided by STD. So that's it. So no biggies. Now we come back to our UCI data sets, and specifically in the way how you split the data. So what are the options? What are the options here? So let's take this first case where we have clear separation on the train and the test data. So how should what would be your approach to standardization? So so we have train and test. So how would you approach standardization here, or data pre-processing? So which of these two files you will be using for computing this mean and STDs?
The trains.
Yes, that would be a common approach. So if you have a train and a test set, let's say, yeah, a common approach would be to compute pre-processing parameters, standardization parameters on a train set, and then you use these parameters to standardize the test set. That is in the case if you are sure that data are from the same distribution. And this is the, I mean, practically important to look into the into data before approaching solving it. So how, I mean, how the values look like for your features. For example, out of these 19 data sets, separated data sets that I referred to, there are some where the testing part has different distribution. For example, the training part can contain negative and positive values, and the test part will contain only positive values. So in this case, so the results can be very different depending on how you train. So basically, if distributions of data in the test and the train set is similar or same, so you the common approach so of values. So compute standardization on train and use for test.
Why can't we combine them and compute?
Yeah, because you cannot combine them. So this by this you will immediately create data leakage. So that is what you want to avoid. So standardization, I mean, by its nature, it looks at data. So in this case, you're kind of peeking into your data set, into your test set.
But when we are standardizing them, then we are kind of removing the correlation between the variables.
No, but you are looking then in the test set.
Okay, but we haven't given it to the model. We are just
No, yeah, but I mean, you transferred information from the test set to the trains to I mean via standardization.
okay. So basically, you're saying that the mean and the standard deviation would be shifted because of the
Yeah.
that might affect the training. Hmm? Hmm.
So now yeah, just a second. So yeah, and in this case, when the distribution is different, so maybe I mean more systematically it would be to do standardization separately on test and the train sets.
Yeah, I was thinking that basically the main problem is the same. We just have two different data sets for it, right? So the underlying features might be the same.
They are, yeah, absolutely, yes. But yes,
So the mean and the standard deviation of the model might of the different variables in the training and test set might be very similar as well. So that was the assumption behind it, but it could be different as well. Yeah.
could be different, yes.
Hmm.
Yes. But then also we can now yeah, we can now also transfer this discussion to the case where we have a single data, and it is we who do the split into the validation and test parts. So in this case, I think a systematically correct approach would be to adopt this different standardization on for training and validation and test parts. So just again to prevent leakage of any kind. So finally, just a second. I want to write a kind of a summary of all this. Can you remind me what I said just to be sure that I have a feeling that I said something contradictory. What did I say about the case with where we do the splits ourselves?
Standardization of each separate.
Yeah, yes. All right. Yes. Yes. Just to summarize, in the separate case, in the case where you have different distribution of values in the train and the test set, so standardize them separately. In the case where you define the splits, we use the standard approach, meaning that, so we use, I mean, all data is in our hands. We use the standardization values computed on the train set and use them for standardizing the validation and the test set. So that is the message. Are you with me here? So the standard approach is to take the train set, compute the standardization, and use this for validation and the test set. So that's what we do. And the same case, if you, for example, choose to be compatible with their method for final testing, so when you do the fold validation, cross validation, so exactly the same approach. So you for a given run, so you take the train part, standardize, and transfer these parameters to the test fold. Yes. Final thing, which leads us to, I mean, to that completes the figure, the picture about the amount of work that it requires for actually systematic evaluation. So many machine learning algorithms, especially artificial neural networks, they include a step of random initialization of parameters. Like if you train a neural network from scratch, you initialize randomly your weight matrices, and in other approaches as well, like even in SOM and such. And in this case, again, to a systematic way of dealing with the randomness is to do several experiments with different seeds, obviously. So because random initialization, especially, so I'm now talking about lab 3, where you need to create a classifier of languages based on random encoding of n-grams. So you may get quite different results from run to run for different seeds. So to get a systematic or statistically correct performance, so you need to run experiment for different seeds and average the data. So and average. So so basically all in all, if you have separated data sets, so you have a training set and a test set, you basically average the results. So when you do the test accuracy over different seeds. In the case of separated, non-separated data sets, so when you do testing by cross-fold cross-validation, four-fold cross-validation, then you need to average across folds and across seeds within each fold. So it is. So and that would be, and now the question is, how many people do that? Maybe not, but I mean, then the question is, maybe not all at least. But the question is how you can trust the results. So in experimental in experimental work, so it is important to kind of get statistically accurate performance. Okay, so and it means that you need lots of experiments. And what I want you to do, especially when you have in mind writing your mini project towards grade 4 and 5, so you explicitly address the question of splits and standardization, and show that you achieve statistically stable results. Then again, so now I have I don't have a good feeling about the time it will take, because it's really lots of rounds. But think about it when you create your experimental scripts. Yes. Evaluating the accuracy or the quality of your classifier. How you do that? So now help me out. So that we will finish with for today. Or accuracy is one thing, but let me remove this stuff. Evaluating classification performance. F1 score. Okay, let's start with F1 score. Yes. So F1 score. It's 2 recall multiplied by precision divided by recall plus precision. So what is recall? So you started it. Recall. Huh? Yes. True positives divided by true positives plus false negatives. Right?
TP divided by TP plus F2.
Yes. Okay. And accuracy then. So it's true positive plus true negatives, and divided by all possible outcomes. Oops. TP plus false negative plus false positive plus true negatives. So that's good to remember. And this is obviously valid for what? For the case of binary classification for 2 classes. So if you work in a multi-class case, so so you truth table or confusion table is basically looks like this: class 1, class 2, class N, or class I, class 1, class 2, class I. So, and basically, this is the true positive case. So you count the statistics, and then you you compute. Basically the average. So you compute the quality metric for each class, and you average it. So and what to take? So if this is a true positive, then what is false negative? So it's a sum of all values in a row, so all misclassifications. And false positive then it's a sum column wise without diagonal element. So but of course I mean this part you will use standard library functions for computing, so that then this will be done for you by Python. Okay, I think time is up, and we continue next week with model-based classification, so SVM. So the answer to Jose is performed in the entire data set. And Junaid, yes, of course. So the clustering DBSCAN is correct. No, it can be done in groups. Absolutely. Or of reasonable size.
Thank you. Have a nice day.
Yeah, bye-bye.